Yeah, so a quick introduction. My name is Stephen Finucane. I'm a software engineer working at Red Hat. In the past, I spent a lot of time working on OpenStack Compute and Nova projects. In recent times, I've been spending a lot more time working on the Kubernetes side of the world, specifically OpenShift and OpenShift support when you run on top of OpenStack clusters. I've also been getting a lot more involved, partially as a result, or maybe as a result of having to actually use OpenStack as a user instead of, the person building OpenStack with a lot of the client tooling. So the SDKs, the OpenStack client project, Keystone Open, whatever else we want to talk about. And because of the kind of crossover between those two projects, I've also been getting involved in Gopher Cloud, which would be the Go-based SDK for OpenStack. So a little bit of background on this talk today, and I'm just going to say from the start, this is going to be a very high-level talk. There's an awful lot of information that I'd like to cover, and I just don't have time to get into the nitty-gritty of it. But we have a forum session immediately after this. I'm also wandering around here for the next 2 days if you want to ask me any questions. And I'm also available on the mailing lists, on IRC, however else you want to reach out to me. So with that said, SDKs. So this is a screenshot from the SDK page on the wiki. So like most stuff on the OpenStack wiki, this page probably should have been deleted years ago. It's mega out of date. It lists a whole load of SDKs that are obsolete or no longer exist. And the only ones that are kind of still alive are these four: OpenStack SDK and Gopher Cloud, both of which I contribute to. And then there's a Java and a PHP SDK. I have no experience with either of these. I can't talk as to the completeness of them, but they exist and they seem to be actively maintained. But the thing that we noticed is that there are an awful lot of dead SDKs. There's a couple of reasons why I think this is the case. Some of them were personal projects that were started and just didn't survive. The developer lost interest, or the developers. This often talked about hype curve, the Gartner hype curve, and OpenStack being in the plateau of productivity, no longer the cool kid in the room. That was Kubernetes. I don't know if that's Kubernetes anymore. AI, I guess. And then also, it is hard work. I can personally testify to this as somebody that has spent the last 3 years trying to fill in gaps in the SDK and OpenStack client for various services. It's been 3 years, we're still not done. And I don't know if we'll ever be done. We're getting there. But anyway, it's hard work. As for reasons why it's hard work, there's a lot of services. There are less services than there was at some point, like various points in the past, but there are still an awful lot of services. Those services themselves all have a lot of APIs. As I said, I worked on Nova for a long time. We have a lot of APIs. I'm trying to document them at the moment, so I know. And then because of that funny thing that we use in a lot of our services, microversions, if you have an API that is bad or crufty, the API never actually really dies. There are a few cases where we have gone and removed APIs, but in general, you add the API, it lives for the eternity, until the death of the universe. There's some other issues which are going to be relevant to what I'm talking about here today. Anyone? Hands up actually, who works on OpenStack as a developer, actually contributing to OpenStack? And who then, I'm assuming everyone else as a user, you're deploying, you're either managing or using OpenStack, I guess. So you probably know then OpenStack client and OpenStack SDK to a lesser degree, they can be very, very slow. It would be nice to speed that up. As I mentioned, the completeness both of Python-based SDKs and clients, but also the other things. I worked on Gopher Cloud. Gopher Cloud has a lot of the important stuff covered, but it might have 30% of all OpenStack APIs. There's a lot of gaps there. There are new languages and new kind of operating environments popping up the whole time. I have a crab emoji in there, so Rust-based tooling, this sort of thing. And then from a service perspective, OpenStack is old. It's been around since the early 2010s. A lot of the services use web frameworks and libraries that may have been cutting edge at the time, but no longer are. Things that have either been deprecated or are effectively unmaintained at this point. It would be nice to have a transition path to get off of these web frameworks. So we sat down, we being the SDK team and various people in our orbit, we thought about it, we gave it a little more thought, we considered giving up multiple times. This has been a multi-year effort, but we eventually provided a solution to how we go about addressing this. Hence our talk today. So the first of these, first part of this talk is OpenAPI. So OpenAPI, hands up who is familiar with OpenAPI? Who is familiar with Kubernetes? And Kubernetes APIs. So if you are, you're familiar with OpenAPI because Kubernetes publishes OpenAPI schemas for everything, I think. So OpenAPI, it is a superset of this thing called JSON schema. It allows you to describe an API in a declarative manner, typically in JSON or YAML file formats. It has built-in support for extensions. This is going to be important later on. And there are tools and tooling available in multiple languages for doing things like validating an API or a client, request responses, this sort of thing, against a schema, validating the schema itself, generating documentation, generating clients and servers, all of this stuff. This is the part of what they call the pet store demo. It's a bad demo, it's a bad example of OpenAPI, but it is the thing that you will find if you go and you look at the OpenAPI documentation or its predecessor, the Swagger API markup language. So a couple of things that are important here. OpenAPI 3.1, again, another thing that will be important in a moment. You'll see that there is the ability to embed metadata about the API itself, i.e. the licensing around the API documentation, an example server. And then you've got things like it's RESTful, so it expects things to be path-based. So the example that's given here is a pets API. You have a variety of HTTP verb operations, get, post, head, etc. And you are able to describe what those things look like, parameters that you can pass in, responses that you get back, all of this sort of stuff. It's very verbose. It is quite hard to write if you were to do it by hand, but it has very wide adoption across, say, most of the ecosystem now. It is what's used by GitHub to say, for example, document their APIs. I think AWS uses it. As I said, Kubernetes generates open API schemas for all of their APIs and so forth. So anyone that's been around OpenStack for as long as I have or longer will ask the question, haven't we actually tried this before? And I'll share these slides afterwards. The answer is yes, we have. The earliest reference to this was back in 2014, which is a good decade ago, back when OpenAPI was called Swagger. But there were a few things that have changed in recent times that allow us to actually go about trying this again effectively. So go back to these points that I mentioned earlier. The first thing I said, OpenAPI 3.1 was relevant. That is relevant because this is the first time that we have a version of OpenAPI that is a full superset of JSON schema, i.e. it builds on top of JSON schema and it doesn't do things in a different manner. There are a couple of examples around for this with regards to how it treats nullable properties, stuff like that. But the fact that we are able to take JSON schema and combine various JSON schemas into something and eventually get layer other things on and eventually get OpenAPI is going to be Very, very important, as we'll touch on in a moment. The other thing, which isn't recent, this has always been the case for OpenAPI and Swagger before, is the ability to add on, tack on extensions. Other clouds use this, we are going to use this ourselves down the line. So that brings me on to the next part of this talk. Again, we're focused on OpenAPI here, which is the code generator project. So the code generator project is, I feel like a bit of an imposter talking about this. This is actually one of my upstream colleagues, if you will. His baby, we'll say, Artem. But this is a project, as it's described there, to effectively go and automatically generate OpenAPI schemas for projects. So the way that it goes about doing that, it can generate OpenAPI schemas, and it can generate bindings in chosen languages, including good languages like Rust. This is an example of one of the things that Code Generator is able to generate at the moment. So this is a snippet from a generated OpenAPI schema for the Nova project. So this is the flavor access thing where you designate which projects you would not have access to a flavor. All of this stuff is completely auto-generated through inspection of both the code and documentation, which I'll touch on in a moment. I have a few things stripped out of here just to allow me to fit it on a presentation in a way that you can actually read it out at the back of the room. But we have got this to the point where we're able to, with additional metadata layered on top, generate clients in Rust that you can actually talk to OpenStack APIs with. For examples of that. How does it actually go about doing it? So the first thing is it inspects code itself. So if I go back a few slides, no, didn't include a snippet of that. There's about, I think there's about 6 projects that it currently supports. Nova, Neutron, I think probably Octavia, Vanilla, Cinder, and I'd say Glance. There might be other ones in there. It has boutique code written for each of those to figure out where the list of all the available API routes are, map those to the actual methods or classes that are responsible for processing requests and returning responses, and then generate the OpenAPI schema from that. It also does, so this is an example of kind of stuff that it's able to pull out. I'll go into that in a moment. It also inspects documentation, with specifically the API ref documentation. This is kind of gross the way that it does it at the moment, because you need to go and build your API ref documentation as HTML. It will then use beautiful soup to parse that HTML, convert it into Markdown, because OpenAPI descriptions have to be marked down, and then inject all of that stuff in. It's not very pretty, and we'd like to go and improve that. So going back to the inspection of code, the things that it's looking at, like I said, it has boutique code in there for each service. Because every service a couple of the services use the same web frameworks, but most of them are using different frameworks. So, for example, Nova and Cinder use a library called WebArt, and another library for describing your WSGI objects. And then it uses another one called Routes for describing the actual how you do API routing. By comparison, Neutron I think uses Peakman. Keystone uses Flask. All of these different services use different things. We need to be able to handle all of those at the moment. But once it has those, I mentioned that JSON schema was important. So this is another snippet, this time from Nova, of that same flavor access API, where we have these schemas here. So this is a schema for the query string parameters that are able to be passed through to this. So we've had this around Nova for probably about 6 or 7 years at this point. We use JSON schema to allow us to validate what a user gives. So that's usually both query strings and requests. And because OpenAPI 3.1 is a full superset of JSON schema, specifically 2020-12, we're able to go and take these JSON schema objects as they are and pipe those in. So that's the code side of things done. The documentation then, like I said, comes from the API ref docs. A couple of issues with that. I said that it's generated HTML and parsing that to generate Markdown. The reason it has to do that is because the API ref docs are all written as Sphinx extensions and they all use restructured text. So they're designed to be human readable as opposed to machine readable. This is less of an issue for Nova, but it is certainly an issue for some of the other projects, that the documentation itself can be incomplete or outdated, missing things. As I mentioned, it uses restructured text. It also we don't have an easy way at the moment of verifying what the API ref doc, how the API ref docs say an API works is actually how it works. And then if we were to use OpenAPI to describe all of these things using the code generating project, we would end up in a situation where we have schemas living in a different project. Again, anyone that has been around OpenStack for a long time will remember the days of having the docs project or the docs SIG being a separate team from the development teams. When we shifted all that documentation into the individual project trees, the amount of stuff that we found in there that was either outdated or complete lies was quite surprising, quite interesting. So it's not something that we want to do. We want our schemas to live inside our projects, and we want to be able to verify our schemas or our OpenAPI schemas against the actual code. So the solution to that is multi-step. So the first step of that is to double down on JSON schema. So I said, I give an example there of us using JSON schema in the Nova project to validate the query string parameters. And as I mentioned, we also use it in some cases to validate the request bodies. Why not use that to validate the response bodies as well? So the idea behind this is we have a known set of responses that we should be given back. They're obviously going to be microversion dependent with some APIs, not so with other APIs, depends on the service. But we have an idea of what the API should look like. So why not go and write JSON schema that actually describes those, and better, when a certain config option is enabled, actually go and verify the responses that the code is generating against those schemas to make sure that our schemas are actually, not lying effectively. So that's what we've started doing. So the first stack of this has been pushed up against the Nova, Vanilla, and I think Cinder projects. All the groundwork has been done for Nova, and probably now in the next cycle. What's the name of the e-cycle? Have we settled on a name?
Oh yeah.
Whatever the.
Let me try to find here.
Yeah.
Not just numbers.
Yeah, they come up with one. They come up with a name as well. So whatever the e-cycle is going to be, in Dalmatian we got a lot of the groundwork done and a lot of the missing query string schemas and the request body schemas added. In the e-cycle, we will be adding or merging the stack of patches that allow us to add these things, response body schemas. And it's not just, like I said, we have Nova, Manila, and Cinder, the patches that we're proposing it. So this is an example from Manila, which is the shared file system project. Again, exact same thing. Manila wasn't using any JSON schemas prior to this. So we have carte blanche to go and make whatever changes we need to do. So we're mentoring students.
Epoxy.
I do epoxy. So we're mentoring students to actually go and add these schemas. We have maybe 3 APIs covered at the moment, and we're rapidly burning down the list of other APIs. And again, it looks the exact same. One little nuance on this is Manila. We're actually using the API documentation to pull in descriptions for various parameters rather than having to duplicate stuff, but it's an implementation detail. And the beauty of doing this is by setting a config option, which we don't enable by default because we don't want to be returning HTTP 500 errors because our schemas were wrong. But by setting this config option in our test environment, we're able to verify that our schemas actually check out, both in a unit test and functional test environment, projects that have functional tests, but also in an integration test environment, i.e. if you run Tempest, you should be able to enable these schema checks, and if your schemas are wrong or out of date, it'll flag. So that's the first step. The next step, which is the thing that we're currently in the process of working on, is the variety of OpenStack extensions. So the OpenStack APIs do a couple of weird things that other APIs don't tend to do. The first of these is microversions. I don't think any other API that I'm aware of does microversions. I suspect everyone in this room is probably familiar with them. If you're not, the idea of a microversion is that we never actually remove anything completely from any microversioned API. Instead, we introduce a new version, so 2.88. That will remove something. If you request the previous version, you'll get the previous behavior. And in the case of Nova, I think we're at about 2.96, so that's 96 revisions to the API. And with a few very limited examples, we have never actually removed anything outright. So trying to document that this is not something that OpenAPI supports natively, and trying to document that is a challenge itself. We'll touch on what we're actually doing about this in a moment. Another thing that we do, unfortunately for our sins, is we have RPC style APIs, also known as action APIs. So this would be, for example, the server reboot API in Nova. The way that works is you post to a /action resource with a particular formatted body, and you will get a special response back, and all that it'll look for is it'll look at the actual body, effectively like JSON RPC or XML RPC. Again, OpenAPI is designed to be like pure RESTful APIs, so we need to layer stuff on top that will allow us to do the mapping, effectively map a request to a response for action style APIs. Yet another thing, we don't have fixed policy, we have configurable policy. So if you look at the API documentation that we have, a lot of the docs will say these are by default admin only APIs, but that is entirely customizable depending on your deployment and your policy in action. This is something that we need to layer on top because it is a very relevant thing when it comes to describing an API. And then this is not really OpenStack specific. This is more of an issue with OpenAPI itself. It is a very good tool for describing things. It occasionally falls down when it comes to actually generating code because it misses some of the nuances that are, needed to generate meaningful code, whether that's a server or a client. So you do have to layer on some kind of hints on top. But all of this is completely doable. This is an example because we're still working on this on the OpenStack side of things. We're currently in the process of adding all the JSON schemas. This will be step 2. This is an example from the AWS APIs. What it actually says, what it means is kind of irrelevant. The fact is that they have these things laid in there to allow them to, with supporting their own tooling, to allow them to add this additional context or metadata that is relevant. When we get to that, the final step, I don't know when we'll eventually be able to do this. Hopefully some of these will be able to happen sooner rather than later. But the final step will be to migrate a lot of the tooling that we have across. So Tempest, for example, Tempest actually has a lot of these JSON schemas already in tree or taken over in Cinder. We would like to get those out of Tempest once they're entirely in Nova because they don't need to exist there anymore. Tempest can just enable the relevant Nova configuration option and run tests that way. As I said, all of our API ref docs at the moment are all written in restructured text with Sphinx extension, specifically this OS API ref extension. We'd like to kill that and use OpenAPI entirely. And then, as I mentioned, clients. it would be really nice to have a client that didn't take, you know, a minute to list all the instances in like our entire internal deployment of OpenStack in Red Hat. Yeah, you don't list instances or images because it takes a long time. So that's that. The other side of this talk, these are kind of, I realized when I submitted this that these are kind of tangentially related, but because they all revolve around OpenStack SDK, and there are some links here I'll go into, they've been thrown into the same talk. The other thing that we're working on, though, in the SDK team is type hinting, adding type annotations to the clients. So this is something that's been around Python since I think about Python 3.5. Introduced in that PEP, it's been expanded in 2 or 3 dozen PEPs since that, and it's still being expanded. I get the impression this is the largest area of kind of ongoing development within the Python upstream team at the moment. For anyone that doesn't write Python code that much, or spends a lot of time with type hints, effectively allows you to annotate put type information into your code and say what variables should look like. This is a really naughty example. Effectively, we're marking up this name parameter saying that it's a string, and we're saying that the method returns nothing. A more useful example, but still quite small because I can't put thousands of lines of code up here, is this code from the OpenStack SDK. These are formatters which we use to convert between values that our user will give us or that the API gives us that aren't normalized to a Python-like normalized version. So this bool string thing here, unfortunately some of the Nova APIs in the past, instead of returning true or false values, they returned yes and no values or y and n values or whatever. These things exist to allow us to convert to proper Python types. So we have the ability to layer on things onto this. This is using generics and it's using type aliases and various other cool little things. The idea, though, is it gives us a few things that kind of tie in quite nicely with OpenAPI. Like I said, nothing really to do with OpenAPI, but helpful in many ways. One of them, if you're using the client tooling as, say, an end user, if you're using, so I use Vim still for my sins with the AO plugin, but you can, if you're using VS Code, if you're using PyCharm, whatever else, if you have a language server protocol, LSP thing installed, server instance installed, you get auto completion by adding all this stuff, which is quite nice. You also get a whole load of additional information about potentially incorrect code. It's been very interesting adding all of these type annotations to projects like Nova because we found a whole load of weird corner cases that we weren't addressing previously. Going back to this, the bool string, it expects a string and it returns a bool. In this case, we're passing in an integer instead of a string. You pass it into MyPy, which is one of the type checkers. It'll tell you that it's got an incompatible type. Pretty handy from a developer lifestyle perspective. Whole load of other stuff it lets us do, remove a whole load of unit tests that are purely related to typing, better understanding legacy code, cross validation with the types in the OpenAPI docs, which is where that tangential connection comes from, and then actually helpful docs. And the places you can find these in OpenStack at the moment, we have initial hints added to the SDK. We have some less added, fewer added into Nova and Cinder, but there are a lot more coming for some of the other libraries like Keystone Law. So keep an eye out for those. So to conclude, OpenAPI is coming to OpenStack. Typing is coming to OpenStack. I really like it if rough format and black come to OpenStack, but I've realized there's not a lot of OpenStack developers in here, so I'm talking to the wrong audience. Want to know more? These links are here. I will put this stuff up on my blog, which I hope I have a link to somewhere in here. If not, we're available on these channels. If you would like to get involved, please give us a shout, catch me over the course of the week. We have a session straight after this. I will happily go into more detail on this. And otherwise, thank you very much for listening. Hopefully that was useful. So we have 1 minute.